Good morning and welcome everybody to this webinar. And let me introduce myself. I am Luca Dotto and I am Country Manager for Hamilton Process Analytics for the Western European territory. This webinar is one of a series of webinars that as Hamilton we started, now it's 2.5 months to stay close to our customers during this pandemic lockdown. And we are continuing, even if we hope that this is going to an end. The topic of this webinar is our Incyte sensor, and which is used to monitor viable cell density in a bioprocess. This webinar is, let's say, a joint webinar between one of our application specialists, Jochen Uhlenkuchen, you already see the picture, and one of our customers, who is Andrea Beinemer, working as a biostatistician for Richter Gedeon. Richter Gedeon is a biopharma company in Hungary, our customer. She will explain how they successfully introduced and implemented this sensor to monitor this parameter, viable cell density, among the parameters that they use to check that the bioprocess is going as it should be. The presentation will last around 30-35 minutes, and at the end of it, you can submit your questions, or you can submit your questions even during the presentation. There is a button, Q&A, at the bottom of your screen. You can press it and write down your questions there. At the end, Andrea and Jochen will answer the questions. One more thing from my side, towards the end of the presentation, my colleague will launch a survey. So you will see some questions appearing on your screen. You can be so kind to answer them. It's about how you found this webinar and what is your interest in sensors and process analytics. That's all from my side. So, Jochen, I leave the word to you.
Thank you very much, Luca, for the friendly introduction. Yes, my name is Jochen Uhlenkuchen, and I'm a biologist by profession and have been working for decades on the question of how best to count cells. I started with automatic counters based on a trypan blue staining count, and these trypan-based counters are great products, but the basic disadvantage is that they can only measure offline. And today this seems a little bit antiquated, because today there are probes available that allow inline measurement, and I would like to talk about these probes now. So before I start, I will give you some facts about the Hamilton company on one slide promised. This is the slide about Hamilton. So Hamilton was founded by Clark Hamilton in the 1950s and is still owned by the family. So we are still a family business. But we have grown strongly since then, and now we have over 30,000 employees, and the headquarters are in Reno, Nevada, and in Bonaduz in Switzerland. We have also 6 production sites and many regional offices worldwide. And Hamilton, so I forgot the pictures of our nice headquarters here in the mountains of Reno and Bonaduz. And as I said, we have 5 divisions: laboratory analytics, robotics, storage, medical, and process analytics. And I will talk about the products of process analytics today. So you may already know some of the Hamilton sensors, and you may be using them. We have sensors for pH, DO, conductivity, and cell density. And of course, we have all these accessories around the sensors as calibration standards, housings, and transmitters. And about 10 years ago, Hamilton developed the unique Arc sensor head and the Arc Air software, and gradually equipped almost all sensors with this innovative technology. And the Arc technology makes your sensors or our sensors intelligent, and then brings a lot of advantages for the user. The required electronics are now completely contained in the sensor head, making an extra transmitter unnecessary, and that means data can easily be transmitted to a process controller, and this can even be done wirelessly via Bluetooth here as an option. And the Arc technology simplifies the work enormously, as it allows easy calibration and maintenance of your probes and an automatic documentation. So a lot of advantages and benefits for the user that is using these Arc technology. So let's now talk about the measuring of and controlling of cell culture and fermentation, which is a complex thing. And you would be probably very surprised if I would ask you how many times a day you measure pH. Of course, you do this online, and other values such as temperature, pressure, oxygen content are also measured online, so that your cells are doing well. But surprisingly, these very cells, the real and actual engine of your production, are still measured offline. And many methods are common for these cell measurement or cell counting. So the worst case is here the manual counter using a microscope and counting cells by hand. It's a little bit better to do that with a TruePalm Blue based automatic counter. Other people are using turbidity, especially those people working with microbial fermentation, or they are measuring cell dry and wet weight. But that will lead to a couple of disadvantages, and everyone knows about these drawbacks of offline measurement. You need consumables and reagents. You have to maintain the automatic counters before and even after measurement. You have to take samples and prepare the samples, and that costs labor time for counting, analyzing, and for the cleanup afterwards. And it's really easy to avoid all these disadvantages. Online monitoring allows an early detection of process deviations. You can reduce labor and maintenance. You can lower your contamination risk. And for that reason, and of course, you can increase the product yield and the quality of your product when you are using an online sensor like the Incyte Arc. The Incyte Arc is a permittivity sensor for viable cell density. So we are measuring viable cells. We cannot detect dead cells with this kind of sensor. And by the way, there are different expressions available for the same measuring principle. Some people are talking about capacitance measurement or dielectric spectroscopy, but these are just different names for the same technology. Let's talk about the basics of the measurement. This is the sensor. This is an Incyte Arc sensor. And here we have two little cells. And in the cells, this plus and minus, we have dissolved salts. So plus or a positive or negative charged ions, particles in the cytoplasma of the cells. And we have a random distribution of these particles. And let's see in detail. This is the tip of our sensor, and we have four little platinum electrodes here embedded in this tip. And when we apply a current to these electrodes, an electric field will appear. And when it happens, the ions will move. The negative ions will migrate towards the positive pole, and the positive ions will move to the negative pole. And what we get as a result is a polarized cell. And when we stop that, we get a relaxation of these ions, of this polarization, and that will lead to an electric pulse. And this electric pulse is linear to the cell volume, to the viable cell volume. That means as more cells we have and as bigger they are, as bigger is the pulse and the value of our measurement. I hope that's clear. This is in principle that's what we are doing with this kind of sensor. And here we have some specs. This is a brief conclusion of the technical specifications of the Incyte Arc sensor. So the sensor itself is available for a DN12 port. For other process connections, we are offering fittings and adapters. And we have 4 different immersion depths from 120 up to 420 millimeter. And I would like to point out here that the sensor is very robust. So it is designed for pressures up to 12 bars, and it can also be autoclaved. The measuring range is wide. For mammalian cells, it is from 500,000 cells per milliliter up to 8 times 10 to 9. So we have a very broad range here for mammalian cells. These are the specifications. And I mentioned already the Arc technology. And this Incyte sensor is available with the Arc technology as well. And this brings some benefits for the user. I will show you some of them. One is about the data transmission and integration. So the sensor offers as a standard a Modbus connection to a process controller. To use it, you need only a suitable cable. Additional software, hardware, or licenses are not necessary. In connection with an optional Bluetooth head, an analog 4 to 20 milliamp signal can also be used, and this allows the measured values for cell density, conductivity, and temperature to be transmitted to an external system. So 4 to 20 milliamp is also available. And last but not least, all measured values can be transmitted via OPC to a process controller or to a SCADA software. So OPC connections sometimes requires some efforts and expertise. Hamilton therefore offers a very convenient and simple solution, and this is the Modbus OPC converter, which allows also for non-IT specialists to connect up to 4 different probes to an external device via OPC. So this is an external device for a very comfortable OPC connection of 4 sensors to an external device. Bluetooth, I mentioned Bluetooth already in comparison with the analog transmission data output. But of course, the optional converter is designed for a wireless transmission of information to a mobile device like a tablet or like a mobile phone. And this is very helpful to get a quick overview during the running process and also in case of troubleshooting. You can see the sensor history, the configuration, the current status, and of course the online measurement data. And again, it's very helpful in case of troubleshooting or for a quick control. The internal memory of the Incyte Arc is also a very helpful feature because all measurement data can be stored on it in this internal memory in the sensor head, parallel and independent of the data transfer to a process controller. If you have some technical problems with the data transmission, the data on the sensor are safe and securely stored and can be evaluated later, for example, in Excel. It's quite easy to convert the measurement signal, which is given in a very strange unit in picofarad per centimeter, to another more common unit like cells per mil. And when you do so, the R square value for this correlation is usually very close to 1. That means the correlation works very well. However, there can be differences between different measurement methods, for example, when apoptosis starts. In order to ensure a precise match of the measured values, in this case, we are offering a modeling software. We are offering the Arc Air data modeling software, which is free of charge, downloadable from our server. And for that software, you can create a model from on and offline values of 5 standard runs. And this model can be stored in the sensor head for reuse in further runs. And then you as a user can decide if you would like to use the raw data or the calculated modified data by the model. And that leads to reproducible and comparable on and offline data over the entire process. And you can avoid these deviations between on and offline values, which we see sometimes at the end of the process, and you can match both signals together. This is also, for me, it's a big and nice feature with the Incyte Arc software. So I will skip this slide here and we'll hand over to this slide here, which is about the CFR 21 Part 11. For all those people who are working in production, the requirements of CFR 21 Part 11 are decisive. These regulations place high demands in data and on data integrity. Due to these restrictions, many devices and routines cannot be used in a production environment. Well, our Incyte Arc probe is well prepared for the requirements of Part 11 and GMP. It offers, for example, a user and user groups rights management, an audit trail, password management, and an electronic signature. And of course, we are providing a documentation and services for the IQ as well. So, and now I would like to, after all this theory, I would like to move on to a practical report, and I would like to give the floor to Mrs. Andrea Weinemer of Richter Gideon in Hungary. She will tell us how the Incyte probe is used in practice. And I will stop now my presentation and then we'll hand over to Andrea. So please, Andrea, continue with your presentation. Andrea?
Yes, can you hear me and can you see my screen?
Yes.
Yes, both.
Great. So welcome everybody. I just trying, okay. First, I would like to say a couple of words about my workplace. The company is named after its founder, Gedeon Richter. Also, the company went through many changes during the century. We have been in operation since 1901. By now, over 12,000 employees are working at Gedeon Richter all over the world. The main three focus areas of the company are original research, women's health, and biotechnology, which I am presenting today. The biotechnology business unit has two main sites in Hungary, an R&D in Budapest and a great manufacturing site in Debrecen that has been in operation since 2012. The Debrecen site has all main functions for the end-to-end manufacturing, from cell line development through pilot scale clinical production to commercial manufacturing of mammalian-based drug substance and drug product in a variety of presentations. Besides handling the in-house project, the site has available contract development and manufacturing capacities. So if your company would be interested in such partnering, the contact details will be available at the end of my presentation. Now, let's go to more interesting topics. Let's talk about process analytical technology. PAT is about the tools which can help ensuring final product quality. The quality can be built into the product through process understanding, process monitoring, and control of the important parameters. Quality cannot be tested into products, it should be built in or should be by design. Product quality is very important for us, so we started to apply the PAT tools in our process and we always trying to follow and keep up to date with the current PAT trends. PAT provides the sensors required to the real-time monitoring and control. According to the type of monitoring, there are different types of sensors. Let's assume we have a production plant with a bioreactor. If the measurement is carried out in the production area and the sample is not removed from the process stream, then we talk about inline sampling and inline sensors. If the sample is diverted from the manufacturing process and may be returned to the process stream, then we speak about online sensors. And in case of at-line sensors, the samples are removed from the process stream and analyzed in close proximity of it. And if there is a time delay, because of the samples need to be sent to a separate laboratory where the measurement is carried out outside the production area, then we talk about offline sensors. How does PAT look like in Gedeon Richter? This is our production plant, which was actually a greenfield investment. We used to log the rabbits on the fields from the office. And we have two production lines here. In case of line 2, our upstream process consists of totally single-use equipment, while the others are hybrid systems. How does our process stream look like? After the shake flask cultivation, the cells to suspension solution is transferred to larger scale bioreactors as part of the upstream process. This is followed by the midstream process and the chromatography and TFF steps, which is the purification part of our process, and the final solution will be filled into disposable bags at the end. Finally, we are giving health to other people and profit to our company. We have plenty of inline sensors in the upstream process. PAT can be used first of all during these steps, but we have plans to apply it also in the downstream process. We can tell that we have plenty of sensors, which resulting a huge amount of data. I think we are lucky that we have a PAT software which offers a common interface for all of these PAT tools. So this huge amount of data can go to our PAT system, and we used to create models from the batches with acceptable quality, because we would like to achieve similar quality during the next fermentation. During the fermentation process, the boundaries of the built-in model will appear, and we can check real time whether the trajectory of our current batch process is inside or outside of the boundaries of the acceptable batches. If the trajectory is close to the acceptance range, then we can click on a certain point and check the so-called contribution plot. This plot tells us which parameter is causing the deviation, and we have time to react. So our process is controlled real time in this way. The real-time control is important because due to the definition of a critical process parameter, these parameters should be monitored or controlled to ensure that the process produces the desired quality. So the built-in model can contain only the critical process parameters. Using inline sensors, we can see real-time if there is a problem with one of the CPPs, and we can do something in time. So our CPPs are monitored using only one chart and also potentially controlled by the help of the operators or engineers. So in this way, we can prove that our process produces the desired quality. We have applied a viable cell density prediction model for it. Our goal is to achieve good product quality and a more robust process. In most cases, the viable cell density, the initial viable cell density is a very important parameter at the beginning of the cultivation phase. So it should be in a predefined range in order to achieve good product quality at the end of the process. In order to achieve this, the VCD values need to be in a certain range at the end of the seed bioreactor 2 step. How can we achieve this? What was our previous method? Let's plot the VCD values in the function of time. The black brackets define the acceptance range, and our condition is that the VCD value should be in this range. For this, we used to take a sample in every X hours, and we used to check the at-line measured VCD value. And if it is outside of the predefined range, then we need to take another at-line sample. But if it is inside of the acceptance range, then the seeding can start. So this is basically a time estimation method. But the process would be more robust if we would try to estimate the VCD values itself and not the time. But we cannot take a sample and execute the at-line measurements continuously. For this, the solution, we have an inline biomass equipment which can measure in every 5 or 6 seconds, and we can monitor the permittivity values of the cultivation process using the Incyte sensor. Using dielectric spectroscopy measurements, we can create a linear model. We can predict the current VCD values real time from the permittivity values. In this way, we can execute the time of seeding with higher accuracy, and we can achieve more robust process and better product quality. Next, I would like to talk about our current solution in more details. Using the inline measured values of the sensor and the data of the at-line reference equipment, a linear model was created. A linear regression line was fitted to our data, which resulted a formula. That formula can be used for the prediction of the VCD values. So from the inline measured permittivity values, we can estimate the current VCD values in every 6 seconds. How big is the difference in the VCD values? I mean between the at-line measured and real-time predicted VCD values. In this graph, the continuous line is based on the created model. So the permittivity values were used for it, which are in picofarad per centimeter, but it shows the estimated VCD values. The red data points are the results of the at-line reference equipment. One thing is very interesting here. If I put all the at-line results from the different kinds of at-line equipments to the graph, then the real-time predicted values, such as the black line, is running in the middle of the at-line measurements. However, the model was building only the data of only one at-line equipment, the red one. This means that the difference between the predicted values and the at-line measurements is almost always smaller than the difference between the different type of at-line measurements. So it suggests that our real-time model can provide higher accuracy than the at-line measurements. In this slide, you can see the differences between the at-line reference measurement and the other different type of measurements. So the result is better if the plotted line is closer to 0. What do you think which is the best? If your guess was the black line, which is the result of our model, then you are right, because we counted the standard deviations for the differences as well. So we can conclude here that the inline predicted VCD values were closer to the at-line reference equipment than other at-line measurements, which is, I think, a fantastic result, and it confirms the usability of this model. We used to apply this model during our further batches in the biotechnology production plant. In these graphs, the black lines are the VCD estimations based on the inline measured permittivity values of the Incyte sensor using the linear model. The blue dots are the results of the at-line reference measurements. The real-time predicted values were quite close to the reference values, which means that these batches can confirm our results. And we can say that our model is scale independent because the model is working for the batches of our R&D department as well. How was the model used during the batches? In this graph, you can see the raw permittivity values itself. So no, there is no model prediction, just the inline measured raw permittivity values. If the permittivity values of the inline equipment is achieved a certain value, then a sample was taken for at-line analysis, and if the result of this at-line measurement was in the predefined range, then the inoculation of the production by reactor could start. So we estimated the VCD values during the process and not the time in this case. This is the VCD estimation method. Let's see the further benefits of the VCD predictions. Using variable cell density models can result less invasive intervention, so the chance of infection is smaller. It results less work, less human error, and less sampling. So the costs are lower, which results higher profit to our company. And all of these because of the real-time VCD predictions. But we haven't reached the top of the mountain with this, because we can improve further our models using only dielectric spectroscopy. I think a big disadvantages of the current method is that the at-line samples are still there. In this graph, you can see the at-line measured and the predicted VCD values. The decreases what you can see on the at-line measured data points in the VCD values should not happen in a normal cultivation due to the general cell biology principles. This is definitely a questionable point of the at-line measurements. We have done a root cause analysis for it, and this can be due to the sample preparation of the at-line measurements. So I would trust in the inline equipment and the results of the model. There is no such a problem in case of the inline measurements, of course. So in my opinion, as a next step, we should forget the at-line measurements and we should just count on the permittivity values if we have enough experience with the appropriate permittivity values, of course. Why is it necessary? Because the errors of the operating personnel, errors of the at-line cell counting methods, and the errors of the model are adding together, and maybe the result would be not the expected. Altogether, we can tell that the at-line measurements have a lot of disadvantages, as it was mentioned before. For example, the at-line sampling is time-consuming, and there is a big chance for human errors as well, as Johan also mentioned it. By using only the permittivity values would have a lot of advantages. For example, reduced risk of contamination and early detection of process deviations and obtain more data. I have created a decision tree in order to visualize the possible seeding strategies. It is obvious that the permittivity estimation method has the most advantages, while that process is less complicated than the others, if you have the correct predefined value. I had a funny story here, because I asked one of the process engineers that in case of our current method, what would happen if the VCD value of the at-line measurement would not be in the acceptance range? And he said with high self-confidence that it is impossible. Indeed, I can tell you that it has not happened until today. So these were the applications of the permittivity measurements for the seeding strategy. Now let's see what kind of further applications are there of the VCD predictions. The automation of feed addition, temperature shift, and inoculation can be also achieved using real-time variable cell density predictions. The inoculation can be based only on the permittivity values, as I mentioned, and the VCD prediction can help also finding the appropriate time of the end of the cultivation. As a consequence, we can tell that the VCD predictions finally result improved process understanding. I haven't talked too much about automation yet. Automation of our processes can be solved in our production plant. Using multivariate data analysis for the multi-frequency permittivity data, we can create models with higher accuracy than in case of using linear models. With our PAT system, we can use these models real time, and there is a possibility to send commands to the process automation system based on the results of these predictions. So in this way, real-time monitoring and control can be achieved in our production plant. Finally, I would like to answer to the main question. Even if the manufacturers of the at-line or offline equipments would develop further the measurement techniques in order to achieve higher accuracy, the operating personnel's error would remain there, and also the sampling with all of its disadvantages would be necessary. So in my opinion, for the first applications, the development of the models, the at-line sampling is necessary. Nevertheless, the most models are scale independent, so maybe it would be enough if the R&D or the pilot plants would develop the models. And in the large-scale manufacturing, we just should apply them or test them during the engineering runs and prove that the models are working well. And finally, the production plants would not need the at-line measurements, maybe just in special cases. So if it, oops, I'm sorry. So if it can be proved that the predictions can be accurate enough in order to apply them in the process, then I think the inline measurements would exchange the at-line measurements in a few years. I think with the inline measurements, the biotechnology and I think I am here. I think with the inline measurements, the biotechnology or pharmaceutical manufacturers would enhance and explain the process understanding and would prove easier the level of process understanding to the authorities. It is also easier to ensure the product quality with the higher and higher level of automation. So all in all, the at-line sensors slowly will be de-emphasized, and the inline sensors will keep their high importance, in my opinion. Let me close my presentation with a quote. I totally agree. Quality can be planned, and most quality crises and problems relate to the way in which quality was planned in the first place. If you are interested in our CDMO partnering activities, please contact my colleague, Mr. János Dombovári. And if you have any questions regarding to this presentation, please send me an email. And now I give back the control to Johan.
Thank you very much, Andrea. It was very impressive, very interesting. And I will go back to my screen. I hope you can see my screen now. Just a second. So here again, we have the email address and also my phone numbers. So if you have a question afterwards, please feel free to contact me. So then we have to say thank you, Köszönöm to Hungary, and see you next time.
Thanks to you, Jochen. Thanks to you, Andrea. And thanks for everybody for taking part.
Thank you
Thank
very
you.
much. Goodbye. Have a good day.
Bye bye.